Just a reminder, we are recording and we do want to get monetized at some point, so.
Yeah.
Do not demonetize us.
Oh, no, I'm a new player.
Someone gets a UTSA chemistry 10. Whoever gets it done first.
Oh my god. It's done first.
With the right answer. We're doing someone $500 to solve this special church. So everyone's returning to council. You got the answer already, Jim?
I wish. I'm getting it.
You're getting there, okay. Keep getting there.
Find your red meal and then it was.
Zoom in.
I don't know if we're going to have
Try to jog your memory. That. Auch Bundesstaat. Even the reps.
Yeah. I know that these. 1.11 competition.
1.11, what comes that? I don't remember doing something. You know where to start. No, you even reactive one and reactive two.
Yeah.
What should you do today?
Fine. But
Yeah, that was do that part. But then, you know what?
Wait, 1 second.
And
the beginning is capital M grams by 1 mole or liters by 1.
what's the equation for molarity? It doesn't always change, it's always one thing.
Then just like grams of a mole.
No. Grams over moles is mole and half. All right, time is up. So basically, we'll go over it now. First, squeeze right over here. All right, gentleman in the front, what's your name? Cash, all right. Let's see if Cash got his money up. All right, what is, you got 31.8, right? And then David, what did you get?
45%.
Interesting. Okay, so 45%. So let's see what we get when we solve that. All right, so a chemistry student who never attends Yellen and Rich's TA sessions is told to find the theoretical yield of the precipitate that forms when 25 mils of a 12 molar solution of sodium iodide is mixed with a 75 milliliter solution of 4 molar lead 2 nitrate. The student forgets how to perform this calculation, and we do it for them, and then we're going to find their percent yield after we do all that stuff. So what's the first step that we always do? Right, so lead nitrate, or lead 2 nitrate is reacting with sodium iodide to produce, what are the products?
Are they precipitate? Sodium nitrate and lead iodide.
Yeah, lead 2 iodide. And which ones are precipitate? Lead 2 iodide, sure. Because that's one of the exceptions for iodides. So that means this is aqueous, this is aqueous because of group 1, and this is aqueous based on the nitrate. All right, now we need to balance it. So this is going to be 2 here. And I'll put 2 there. And we're all good. All right, what should I do next? Find moles, right? Moles of what?
Sodium iodide.
Yeah, so sodium iodide. And once I find the moles of that, what do I do with that?
Multiple ratio.
Yeah, because we're trying to find the what's the special term we use
Theoretical yield.
of we're trying to find the limiting reactant based on the theoretical yield based on the limiting reactant, right? The theoretical yield based on the limiting reactant. This gives me 0.3 moles, and this is sodium iodide.
How do you know sodium iodide is anything, right?
You don't
We-
yet.
Yeah,
And why do you pick sodium iodide?
we have to do it for both of them.
Good one. Start.
And that produces 1 mole of lead 2 iodide. So this is going to be 0.15 moles of precipitate. And then we do the second one. So again, I chose to start with sodium iodide, but I was already planning on doing lead 2 nitrate from the very beginning too. So 0.075 liters times the 4 molar is going to be, what's that? 0.3 as well. And this is PVNO32. We use our mole to mole ratio, right? And that's, in this case, that is 1 to 2. 2 moles. PVI2. So this gives me 0.6. Yeah, you're right. It's 1 to 1. I'm sorry. Looking at the wrong reaction. So this gives me 0.3 moles. Good catch, guys. Moles of precipitate as well. So based on this one, the theoretical yield is always going to be the smaller number, which that tells us the limiting reactant with sodium iodide, right? So we'll just mark this one out so that way we don't we don't use it in the problem. And we just take this one step further. What's the molar mass for lead to iodide? 461. And now he was the theoretical yield in grams, which when we do that. Did y'all get this far? Who got this far? Awesome. Okay. You got the one wrong one? Masses. Oh man. Don't worry. Don't get them wrong on the test, okay? So this is it's not our answer. In green, this is our theoretical yield, which we're gonna come back to and use.
But 461 in grams of lead iodide.
That's lead to iodide, TbI2,
That's 461.
461, yeah. So percent yield is our actual yield over theoretical times 100. So you get, they told us the actual was 22 grams, as seen over here. So that's what we're getting that from, 22 grams divided by 69.15 grams times 100. And this is the moment of truth to see if Pat had his money.
Fire money.
Cash said 31.8, and the answer is, let's see sig figs first. How many sig figs should we have?
I guess two.
Two sig figs. So the calculator says 31.8, but actually it is 32% based on sig figs. So close. All right, don't worry, you get the pen.
I'll give you $10 if it gives you the 5 cents.
Decimal. Oh, you could put 32 decimal or 32%. They'll both be the same thing. So they're the same number. Yeah. Cool. All right. Are there any questions? That was a relatively easy for people that practice. And that's okay. You have 2 more days. Well, 3 if you include the rest of today to study for the exam. So don't sweat it, guys. Although make sure you know your solubility rules. I've been telling you this for weeks now. All right, number 2. The dean of the College of Science told you to find the original concentration of a solution that was used to prepare element 115, which is just cadmium hydroxide. They tell you that 0.5 liters of 10 molar solution of cadmium nitrate reacted completely with 0.5 liters sodium hydroxide. This was the, what was the original concentration of the sodium hydroxide solution? And this is supposed to say solution. I don't have any prizes to give out. Let's see if there's anything in this book. Three minutes on the clock. All right, 3 minutes is indeed up. Yeah. All right. So where do we start, guys? That's what we always do first, right? So if you don't know where to start, just remember step 1 and do your balanced chemical equation. This one is cadmium hydroxide. How do we know the charge? What if they just gave us cadmium, like the name for it, not the formula? How do we know the charge for cadmium is a transition metal? What?
It doesn't have any charge.
Its charge is 1 plus 1, sure. You're not,
Oh, by the subscript of the N.
but I'm saying, what if they gave you the name cadmium hydroxide?
Shouldn't cadmium hydroxide be on the product side, because it says repair element 1.5?
Yeah, you're right, sorry. So Roman numeral for transition metal usually, but cadmium is one of those special elements in the transition metal series that does not have a Roman numeral because it only has 1 charge. That along with silver, scandium, and zinc all are the ones that have a fixed charge. And do y'all remember what those charges are? Zinc 2, cadmium's 2, silver's 1, and then scandium is 3. Yeah, yeah. So there you go. So cadmium nitrate reacts with sodium hydroxide to form cadmium hydroxide, which is going to be solid plus sodium nitrate. And balancing this will give us 2 over here, 2 over there, and we're good.
Shouldn't there be a 2 after the sodium hydroxide, because it's hydroxide is NO3 too?
Hydroxide is OH minus.
I mean, yeah, you have
What?
nitrate.
The nitrate? No, it's a 1-to-1. Sodium has a +1 charge and nitrate has a -1 charge. They cancel out.
And why is there a 2 on the outside on the reactant side?
Because I had to balance it. Over here we have 2 nitrates, but only we had 1 over here, so I had to put a 2 over here.
No, I'm talking about the 2 outside parentheses in the reactant.
Because cadmium is a +2. Did I do something wrong? Oh. So it's just the charges. That's how we're getting to where. Does that make sense? All right. What do we do next? Okay, yeah, so let's figure out what we're looking for. We're looking for the concentration, right? Because it's saying what is the original concentration of the sodium hydroxide. So we're looking for the molarity of NaOH solution, which we're gonna need moles of NaOH. Divide that by the liters of the solution, which they gave that to us here, 0.5. So we can agree that we're looking, in order to solve this problem, we need to find moles of sodium hydroxide because that's the only unknown in that equation. So the way we would do that is,
So molarity is moles over liters.
yeah, 0.5 liters of this is of the cadmium nitrate solution. Multiply that by the 10 molar concentration of that solution will give us 5 moles of, what is that, sodium, cadmium nitrate. And then from here, we just do what we've always been doing for the last few weeks. Couple more days and we'll get into completely new topics. So this ratio is for every 1 mole of cadmium nitrate, there's 1 mole of cadmium hydroxide. And I always tell you that you don't have to write this step out. If you realize it's a 1-to-1 ratio, then you don't have to do that step. It's just, I'm showing you, I'm just writing it out for people that want to see the units cancel out. And then we need we can stop right there, right? Because our desired unit is moles of sodium. I did something wrong. This would be sodium hydroxide. So it's going to be 1 to 2, not 1 to. And today is just been a long day. All right. So this gives me 10 moles of NaOH. All my units cancel. I'm left with my desired unit, which was moles of sodium hydroxide. Plug that into this equation over here, so you get 10 over 1/2, which is just going to give us 20. So 10 divided by 0.5, or you can say that's 10 divided by 1/2, which is just 20. So molarity equals 20 molar sodium hydroxide, which is pretty concentrated. You definitely wouldn't want to go near that solution. All right, that was an easy one. Between 3 and 4, we'll let you decide which one you want to do. Let's come to a consensus first before we all start calculating stuff.
Raise your hand for number 3.
Well, we gotta read them first. Y'all read these?
Yeah. I think you raise hand for number 3.
Oh,
Okay, number 3 or number 4? 3, 4. All right. I think we got more people for 4, so by 1 person. So yeah, do number 4, and we'll go back to number 3. Yeah. I'm gonna go walk around. Y'all ask your questions if you have.
Never mind.
Here, boss.
The Barbie.
Oh, yeah. And what department have it too?
Carbon.
All right, I have another prize for y'all. So whoever gets this one first. The biology pen, so I don't really care for this. Biology.
And Tom, okay. After watching Oppenheimer, the general chemistry student feels like theory will only take them so far. So they decide to go perform an experiment in the lab. They mix 50 milliliters of 2 molar chromium nitrate or chromium 3 nitrate and 50 milliliters of 4 molar lithium hydroxide. Using advanced analytical techniques, including a calibration plot, the sensitivity of 0.5, student wants to determine the concentration of nitrate ion in solution left over after the reaction stops. All right, what is going to be our first step always? Or before balancing the equation, we got to write it out, right? So write out the equation, then balance it. So chromium nitrate, so CrNO3, 3 plus lithium oxide. What are my products?
Chromium oxide.
Or where does sodium come from? Lithium nitrate, yeah, that's one of them. And then what's my other one? Chromium 3 hydroxide. If we were to do our physical states, right? What are my physical states for instance? Like the states of matter. Yeah, they're all aqueous except for chromium hydroxide.
Why do chromium 3?
Because this is something called a precipitation reaction, which is double displacement. Basically, what happens is the anion from this one mixes with the cation from this. So the positive chromium 3 plus mixes with the OH negative. And you just switch the two like that.
I don't know chromium as a charge plus.
Because of this 3 subscripts here under the nitrate. Yeah, for the balanced equation. 1, 3, 1, 3, 1. All right, so 3, 3, and 3 here. So let's check it. Let's check it out. Well, you said 1, 3, 1, 3.
Yeah.
1, 3, 3. Let's try this out. So 1 chromium on the reactants, 1 chromium on the products. We're good. 3 nitrates in our reactant, 3 nitrates in the product. We're good. 3 lithiums in our reactant, 3 lithiums in the product. We're good. 3 hydroxides in the reactant, 3 hydroxides in the product. We're good. All right, so this is indeed the balanced chemical equations. So what is next? Find the limiting reactant. So we're going to multiply our milliliter and molar amounts because that'll get us moles. So 50 divided by 1,000 times 2. We convert the milliliters to liters, right? Because molarity is moles over liters. So once we do that, we get 0.1 moles of chromium nitrate. All right, so 0.1 moles of chromium nitrate. And then, right, since it's a limiting reactant, we have to do the same for the other reactant. So I'm just going to do them both simultaneously. So 50 divided by 1,000 times 4. 0.2. So 0.2 moles of lithium hydroxide. All right,
So. First, if it's asking for the nitrate ion, don't you first decipher whether nitrate participates in.
so it asks for the nitrate ion left over. So basically what it's saying is, once this reaction is complete, how much nitrate do I have? So there's really one of two options, right? So one is if our nitrate compound is the limiting reactant, what will our nitrate ion concentration be?
Yeah.
0, right? Because all of the limiting reactants are zero. But it could be the case that a nitrate compound is our excess reactant. And if it's our excess, then we have to find out how much is in excess.
Right.
So that's the process we're kind of doing. So to do this, right, first what we're going to do is convert everything into our moles of precipitate. So 0.1 moles of chromium nitrate, right? So we see from our mole ratio that for every 1 mole of chromium nitrate, there's 1 mole of chromium hydroxide. So this is a 1-to-1 ratio. Then we do the same thing down here. So for every 3 moles of lithium hydroxide, there is 1 mole of chromium hydroxide. All right. With that being said, what will our limiting react? Lithium hydroxide. So if we do the math again, it's 0.2 divided by 3, which is 0.067. 0.067 moles chromium hydroxide. So since we found out what our limiting reactant was, I'm gonna cross out the top stuff because frankly speaking, we don't need it anymore. So now that we have our moles chromium hydroxide, right? What does the question ask for again? Yeah, that's for the concentration of nitrate. So what do we have to do? Yeah, find the moles of the nitrate from the chromium hydroxide, right? So once we do that, because this will give us the moles of nitrate we use up. So for every basically 1 mole of chromium hydroxide, there is 1 mole again of chromium nitrate. So we see that there is 0.067 moles of chromium nitrate. Is this the final molar or final mole amount of our nitrate ion? Why not? I'm asking, like, there's 0.067 moles of chromium nitrate, right?
Yeah.
Is there also 0.067 moles of the nitrate ion?
Yeah.
Why not?
You would have to multiply it by the nitrate, number of nitrate ions.
Yeah, the number of nitrate ions. So we say that for every 1 mole of chromium nitrate, there's 3 moles of nitrate ions, so NO3 minus. When we do that, we'll get 0.2 is the moles. 6.7 chromium nitrate. All right, so 0.2 moles chromium nitrate, CrNO3.
Is it just, is it chromium nitrate or is it just?
Oh, sorry, just the nitrate ion. 0.2 moles of NO3 minus.
Wait, why did you multiply 0.067 moles of? Why did you multiply by 1 to 1?
Because there's a if you look at the balanced chemical equation, it isn't indicated, but anytime there isn't a coefficient indicated, it.
Yeah, I know that's 1, but what element is the top one and the bottom one?
So, yeah, I don't like to write it out because there's less space, but I should have in this case, so that's my bad, but bottom would be chromium hydroxide, and then the top would be chromium nitrate.
But doesn't the chromium hydroxide have 3 moles?
No, there's 1, if you look at the equation. All right, so you have 0.2 moles of nitrate, right? So how many moles of nitrate ion did I start off with? So if I started off with 0.1 moles chromium nitrate, how many moles of the nitrate ion did I start off with? Yeah, 0.3. So for every 1 mole of chromium nitrate, there's 3 moles of chromium, or sorry, not chromium, 3 moles of NO3 minus. So once that's solved out, you get 0.3 moles of chromium nitrate. Well, why do I keep writing on chromium nitrate? Sorry, 0.3 moles of nitrate ion. All right. Now, I'd like to ask you all this. What does the 0.2 moles of NO3 minus represent?
The excess.
So it's not really the excess, right? Yeah, it's the amount used up. So it's how many, so basically what we're saying is in order to make our chromium hydroxide, we needed to essentially use up 0.2 moles of nitrate. So to get our excess reactant now, we take the initial amount we started off with, so 0.3 moles, and we subtract it by the 0.2 moles. And if we do that, we will get 0.1 moles of NO3 minus ion left over. But are we done here? No, right? Because what does it ask for? The concentration. So what do we do to get concentration? Multiply? Yeah, moles over liters. Yeah, sorry, I'm just kidding. So 50 milliliters, right? So we do 50 over 1,000. So once that is the case, 50 over 1,000 and 0.1 over 0.5, we should get a concentration of exactly 2 molar. So there was 2 molar concentration of NO3 minus. All right, I know that was kind of a circular way of going about things. Yeah.
In the beginning, when we're using the reactants to solve it, why do we use chromium hydroxide to solve water? Because it's the precipitate.
Yeah, it's the precipitate, so that's like ultimately the goal of our reaction, right?
Okay, so it's a small ratio to that.
Yeah. So essentially, what we did, I know that was kind of a roundabout way of explaining. So first step, wrote out my balanced chemical equation, assigned my physical states to everything, because I know that this is a precipitation reaction, in which case the solid is really the only compound we care about. I didn't show it here, but the net ionic equation, it only takes into account the ions that form the solid. So, unfortunately, I had to do some calculations for the limiting reactant, since it wasn't clear which one it was. So that's what this work here was for. So I found the moles of chromium nitrate and the moles of lithium hydroxide I started off with. Then I converted both of those into my moles of products. Because the moles of precipitate ultimately is what is limited by the limiting reactant. So once I did that, I found that lithium hydroxide here was my limiting reactant. So if lithium hydroxide was my limiting reactant, my next step was to figure out how many moles of nitrate were used up. So after that, I converted moles of chromium hydroxide here to moles of chromium nitrate, because that's ultimately what we care about. But it is true that for every, since this is an ionic compound, right? There is basically here there's 1 chromium ion and 3 nitrate ions. So basically what I had to do was multiply the moles of chromium nitrate by the moles of the nitrate ion. Because for the molarity is essentially like 3 times, because you had multiplied by 3. Or that's why you multiply it by 3, because the molarity is 3 times as much as it would be for the regular compound. So once I did that, I got 0.2 moles of NO3 minus. But this represents the amount I used up. And it's the question's asking for how much is left over. So what I had to do then was figure out the amount of nitrate ion moles I started off with. So I did that in a similar fashion. So I started off with 0.1 moles of chromium nitrate, and then I converted that to moles of NO3 minus by multiplying by 3 once again. So 0.3 moles chromium nitrate is what I started, or nitrate ion is what I started off with. and I used up 0.2 moles. So 0.3 minus 0.2, I got 0.1 moles of NO3 minus. But it does, the question is not asking for moles, it's asking for the concentration. That's why I multiplied it by the volume here. Moles over volume, that's molarity, and we should get a final answer to.
Any questions on this problem? It was a pretty hefty problem, right? It's probably gonna be the hardest thing you may see for this exam, okay? There's a lot of steps that went into this. But the bottom line, which is what we've been doing for probably 5 weeks already, 4 weeks, is let's just go through the steps that we do for each of these problems. So what's always the first thing we do? Right, so you'll see that like it's just a game of repetition every single time. So we're gonna write out a balanced chemical equation. And then the second thing we do is we'll typically find the moles, because in chemistry we're going to be dealing with moles, and because our balanced chemical equation is everything's related to each other in mole to mole ratios, that means we're going to be dealing, our units should be in mole. So we find moles, and then we convert to desired unit. So maybe you're given, you find the moles of the reactant and you're asked for the theoretical yield, you would find the limiting reactant. So this is also the time where we should be thinking about limiting reactants. And there's really only 3 ways to find moles that as of right now. And if you're given the mass, the way you find moles is using what? Yeah, so molar mass. And if you're given the atoms or formula units, how do you find moles then? Yeah, so you use this thing here. And the last way, which is kind of maybe new to y'all, is using molarity. That's the other way we're going to find moles, because molarity equals moles divided by liters, or volume in liters. So this is how we're going to find, there's 3 ways you can find moles. Okay, there's 3 ways you're going to see it on an exam question. There's no other way. So remember, find your moles and then convert to the moles of the desired whatever it is. And then you just want to start thinking, maybe it's asking for a percent yield. So in that case, you would just have other information that you would have to be given. So what I'm trying to get at with all this, it's all just the same thing over and over again. And the more problems you do, the more comfortable you'll feel going through all these steps. All right. So just practice, practice, practice. And we're going to do another problem right now. One last problem that you can use to practice. Yeah. So just go through those steps and you'll get a good grade on the test. Guaranteed by Rich.
Yeah, it's
Did anyone solve the problem, by the way? I'm trying to get rid of it. Yeah, you want to practice? It's biology. It might be bad luck, so it's not a test, but chemistry test. It is a matter of one, because regardless, you should get the limit of the reaction should be the same.
Yeah, that's the same environment.
Yeah.
Make sure you say something.
Yeah.
Yeah.
Yeah, the solution.
Yeah.
going on with Bessie's? They got a cricket. What's the difference audio? Oh. All right, one more minute. Who's done? All done. David. Yes. Are you done? No. Why you flop back in that chair? Come on, relax. I was looking at the question. That's one very confused about how is it find the actual or different percent. So what's the division per percentage? It's actually theoretically. Theoretically. And if you keep it at 71, then you have to keep the 100 connection. But if you make it 0.71, then you have to. You can react it. Then actual, it's asking what's the answer. All right, y'all ready to go? Let's talk. All right.
Let's do it. So, a precipitation reaction occurs between calcium hydroxide and titanium 3 nitrate. The percent yield of this reaction is 71%. What is the actual yield of the precipitate when 60 grams of each reactant are mixed together? So, step number 1, what will it be? Right and balanced equally. So, do green for today. Calcium hydroxide, so CaOH2, and titanium 3 nitrate. So if you do your crisscross method, that's TiNO3 3. What are the products of this? or calcium nitrate, so CaNO3, 2, and what else? Titanium hydroxide, so TiOH. If we were to assign physical states, what are states of matter? All of them are aqueous except titanium hydroxide. Aqueous, aqueous, aqueous. Solid. All right. What did y'all get when you balanced the equation?
3, 2,
3, 2, 3, 2. Let's check this. 3 calciums, we're good. 6 hydroxides, we're good. 2 titaniums, we're good. 6 nitrates, we're good. All right. So 60 grams of each reactant is mixed together. What does that tell you all on that? Moles what?
Yeah.
What type of reactant? The limiting reactant. You gotta find the moles of the limiting reactant. So 60 grams of both of them, right? So 60 grams of calcium hydroxide and 60 grams of titanium 3 nitrate. Again, I'm doing both at the same time. So what's the molar mass? Calcium hydroxide? 74. Are there any decimal points after that or no? Always include the decimal points for optimal accuracy.
I got 57.085.
57.
Then you-
Wait, you might, I think you're right, actually. It was 40.
I forgot to multiply the
32.
hydroxide by 2.
Oh, yeah. It should be somewhere around 74, 75. 74.078 grams per every 1 mole. What's the point for precipitation reaction again? Yeah, make it precipitate. So basically, what I'm gonna do is I'm gonna convert my moles of calcium hydroxide into moles of titanium, or titanium 3 hydroxide. So for every 3 moles of calcium hydroxide, right, there's 2 moles of titanium 3 hydroxide. Got that again from the balanced chemical equation. So we're gonna do the same thing to our titanium nitrate. What's the molar mass for titanium nitrate?
Three, 3,
200 seems a bit too much. Oh wait, no, it doesn't. I made a mistake. I forgot to multiply the oxygens by 3 again, so it should be 9 oxygens. I was doing it for 3. So yeah, the 200 range might actually might be right. Plus, all right, I got somewhere around 234. So what was the molar mass with the decimal points again?
233.88.
233.882. All right, 882 grams for every 1 mole. And if you look at our balanced chemical equation again, for every 2 moles of titanium nitrate, or titanium 3 nitrate, there are 2 moles of titanium hydroxide, titanium 3 hydroxide. So again, it's a 1-to-1 ratio. So if we solve this out, what will be our limiting reactant? The titanium? Alright, the titanium hydroxide, some people say, are the limiting reactant. Do you all agree with the majority?
Yeah.
Right, we have one yay in the presence, and, yes, titanium hydroxide is indeed the limiting reactant. So we're gonna cross out this calcium hydroxide work, because we don't need it anymore. So I got 0.257 moles of titanium 3 nitrate. So I know this, right? We're given percent yield, and we need to find actual yield. So what else do we need to find? Theoretical yield. How do we get theoretical yield from the amount of moles we have? Yeah, this should be titanium hydroxide, my fault. So what is the molar mass of titanium hydroxide?
Gonna do.
98.88. Yeah, sounds about right. Should be 98.88 grams. Oh wait, sorry, that should go on the bottom. Bottom. 1 mole has 98.888 grams. So what is our theoretical yield? Sounds about right. 25.369 grams. All right, we're almost done. We have a percent. We have we have a theoretical. How do we get actual? Multiply by the percentage. So if y'all recall, percent equals actual over theoretical. So actual equals percent times theoretical. So basically, we'll do 0.71 times our 25.369. And what was our actual yield? 18.0. Yeah. How many sig figs should we have in our project? 2, so it's just 18, right? 18, and there's stuff after the decimal, so I'm just gonna put decimal. To indicate that there's stuff after it, but they're not significant digits, so we don't care. So 18 grams of titanium hydroxide is our actual yield. Any questions about that? Compared to 4, piece of cake, right? All right, with that being said, see y'all on Friday. We will study up on your stuff. We had fun making some difficult problems. So yeah, prepare to I don't know, beat your major.
Who memorizes what good was what? I would try. No? Oh, not the basic number. Okay. Well, we also have 2 more days to plan that. I'll do that. I did good job.
So, yeah, I